Okay, so yeah, this is going to be a mathematical model, and you know how you do the implementation to get the effects that we're predicting under this model. Okay, so did it move to the next screen?
Yep.
Okay, yeah, so this is based on our DARPA project and our JANF presentation. The JANF presentation was classified, you know, and our DARPA project is listed as sensitive military technology, so it's covered by C. So I'm kind of limited on what I can present here, but I can present enough. And no one's reviewed this PowerPoint, so we're just going to go with it. And the the JANF presentation was the 65th JANF Propulsion meeting that was held in Long Beach, 2018, and we were presenting a paper on how we would break Green's reciprocity to generate an external force on a device that you could use for propulsion. And that got us a DARPA contract to build a device for DARPA using relativistic electrodynamics and an exotic propulsion. And what we had to do in this project was we had to lay out the mathematical method that we would use, what kind of effects we would expect to see, and how we could use them to make a device. And that's where we are in the middle of this project right now. So if I start from the beginning, right now we have two fields in physics. We have the electric field and the magnetic field, and they have two sets of equations that are separate. So originally they were thought to be two independent fields, but James Maxwell, James Maxwell unified them. And these equations that I'm showing here are not really Maxwell's equations. What Maxwell did is he used some mathematical construct called a bicquaternion that derived the equations from the potentials. And I don't really expect anyone to know that or how to do that kind of math. But these equations are really Heaviside and Gibbs reformulation. And what they did is they took Maxwell's original derivation and took his 20 equations, 20 variables, and Oliver Heaviside employed the curl and the divergence operators, vector calculus to reformulate 12 of these 20 equations into 4 equations with 4 variables. And by the form which they've been known as Maxwell's equations, but they're not really the equations that Maxwell produced. And always the big question has been, what happened to the other 8 equations? And this is what happened to them. So on this page, the first 4 lines is the modern way that we would do James Maxwell's derivation. It's known as the Clifford algebra. And it's much simpler to use, but you know, I'm finding out that very few people, unless they're in mathematics, know how to do this kind of derivation. But what this basically says is we can take the potentials, which was the magnetic vector potential, and we can derive 3 equations from it. The first 2 equations, equation 1 here is the electric field equation, and the second equation 2 is the magnetic field equation. And both these 2 equations have the same term in there, the magnetic vector potential. So that, from Maxwell's point of view and physics point of view, shows that the magnetic field just must be an aspect of the electric field. This basically unified the equations, and what this resulted in was the view that the magnetic field is not a separate field from the electric field. It's just another aspect of the electric field. But the problem with his derivation is he generated this third equation, which is called the magnetic scalar potential. And this has some effects. I mean, it still has the same magnetic vector potential. So this basically says this equation could feed back onto the other 2 and virtually make them unsolvable, because you know you could have an electric field that generates a scalar that feeds back to the magnetic field that could eventually feed back to the electric field. So they had to remove it because nobody was really seeing the effects from this third equation when Maxwell did his derivation in the early 1900s. So the magnetic scalar potential is the equation up here. The meaning of it was the point space that's tied to an inertial reference frame. Okay, a changing potential will produce a non-zero value, but a non-zero value of what? Because the units in here don't really tell you what that value is going to be. And the magnetic vector potential produces a non-zero value in the direction of a vector. So And I already mentioned here, this is a problem. This is going to generate these unseen feedbacks. And before 1960, the magnetic vector potential was never measurable. So, there's another reason. If you can't measure it, it must not really be real, or you can't really use it. And then plus Oliver Heaviside and Joshua Gibbs, the original creators of Maxwell's equations, the authors of today's equations, viewed the fields are real and scalar potentials in these equations were just mathematical abstractions with no real meaning. And so that's where electromagnetics is today. It's based on the fact that potentials really have no real meaning. And so to get rid of that equation, they apply the gauges. And the first one is the Lorentz gauge, which is basically created, it just takes the scalar and says it's zero. And then we basically get this equation here, which says is the Lorentz gauge. And then they can also use the Coulomb gauge to get rid of the rest of these terms by setting the magnetic scalar to zero and the term, the changing potential at the time, to zero for electrostatic charges, because by the definition of electrostatic, they're not changing. So between these two gauges, we're able to eliminate the scalar potential. And that's the way electrical engineers have been using it for the last 100 years. And what this
There's
is
also
saying,
the unified velocity gauge, where there's just one gauge that incorporates both the Lorentz and the Coulomb.
Yeah, that's a different gauge entirely. So, but that does unify the two of them, takes the two aspects, and basically it's just declaring the scalar potential to be zero.
Richard, and I should apologize for interrupting. If I could jump in really quick. So Eric Hermanson has been working with Richard Banduric on this. They've been collaborating together. And so that was Eric that you just heard. Eric, thank you for joining us.
Yep,
thank you, Tim.
Eric. Okay, so by applying the gauges, what you're basically saying is the scalar magnetic potential is declared to be zero or a constant using the Lorentz gauge and the Coulomb gauges. So it's just basically flat. So that's saying the whole universe, or at least the universe around us, is the magnetic scalar potential is at the same value, so or it's flat. And these gauges are acceptable for electrical engineering because electrical engineers don't see the effects of this scalar. Of course, it's not valid to just use these gauges for physics, and that's the problem here. One thing is heard in 1960, Androff-Bohm effect confirmed that these magnetic scalar potentials were physically real and you can measure them. They would take a coil where A is not zero around the outside, but B is zero. So they would pass a beam to either side of this coil and then reconverge it, and it should be the same, but it doesn't. So you have the beam changes its phase. So these magnetic potentials are affecting a beam of electrons in this case. So at that point, the Coulomb gauge and Lorentz gauge are invalid. I mean, they must only be valid under certain conditions. And that should have been fed back in physics way back when, in the 60s, especially since this is not the only experiment that's proved this effect, that the scalar potential is real, it can be measured. This is just one of the first ones. So this again said, basically the gauges must be invalid under some conditions, because physics or electromagnetics is saying that the gauge is flat here as this little graph, but really, in that particular instance, we get a graph to something like this thing, a little hat guy. So something's there, and we should be able to use it to, affect, motion. And that was one of the reasons we started on this DARPA project. So the conditions that allow the electric scalar potential to be removed out of electrical engineering is having a connection somehow, a path to ground. Because we're right next, we exist on a big conductive sphere. So this big conductive sphere has an infinite supply of electrons, and it can absorb an infinite number too. So this sphere is like a big sink and source that you can use to try to keep some system of currents neutral. So almost every system today is grounded somewhere, or they have an indirect path to ground. And that's one of the reasons that you can eliminate the magnetic scalar potential. Another thing is the source impedances. If you have all our source impedances have, you know, an impedance to some low value, because if it didn't, it wouldn't be able to drive any current from the way our sources are built today. So that's effectively going to ruin the magnetic scalar potential too. And then the third thing is long, thin copper wires. You're not going to see longitudinal field components in a long, thin wire as compared to the cross product components, because the area around the wire is so much greater than the area looking in the ends of the wire. So usually when you have a long, thin wire, the difference is thousands of times. So you virtually can ignore any scalar effects that are normal electronics. So the source, so we have to go into the source of the magnetic force, which is the magnetic field was created to describe the magnetic force originally back in the 1800s. So today's electromagnetic vector equations, when two wires conduct an electrical current, a magnetic field is generated, a magnetic force arises, as described by that formula. We have two currents, and basically this is the mathematical abstraction we use to represent the magnetic field. But if we look at these two equations, we have current one, current two. What is current? A current is just coulombs per second passing a certain point. Well, that coulombs passing a certain point can be flowing really fast or really slow. So in copper, the drift velocity, which is the speed that electrons move in a wire, is really, can be as low as 1 millimeter per second or as great as maybe 10, 20 millimeters per second. But that's really slow. But you could have current flowing through another type of material that's moving at 10,000 meters per second or 100 meters per second. And now the current density of the wire is going to be less by that same amount, and you'll still have 1 amp going through that particular point. So I could have 0.01 coulombs per meter current density with a velocity of 100 meters per second. That would give me 1 amp flowing past the point. Or I could have 1 coulomb per meter in the wire flowing at a drift velocity of 1 meter per second. And that would give me a current of 1 coulomb per second or 1 ampere. And there's no efforts made to distinguish between those two currents. And when we look at how the magnetic force is generated, those are not the same currents. They don't generate the same type of field. So reciprocity. Reciprocity states that integrals over a space will all sum together. So the requirement forces the electric and magnetic fields for multiple charges or multiple sources of the magnetic field to all sum together or follow the rules of superposition, which basically means if I got a magnetic field from a chunk of a magnet and I got a magnetic field coming from a coil of wire, at any point in space, I can just sum those fields together and say they're good. So if I had an electromagnetic that was north and south and another magnet that was north and south, and I put the two norths together, electromagnetic says that those fields should obey the rules of superposition. So you can just add them up at any point in space to calculate the force. But that's not necessarily going to be true here. Because really, once 1905, relativity was proven to be true, what happens instead is when an electric current is flowing down the wire, it's experiencing time dilation and length contraction. And the length contraction that the electric current observes is this term here on the top, v squared over c, 1 minus square root. And what it basically says is, if I have, a coulomb of current flowing down the wire at a certain velocity, all of a sudden it's going to look like it's a greater amount. The current density is going to look like it's going to increase. Until you hit the speed of light, then it's going to be infinite increase. And it's not that the wire is actually increasing in density, it's because of the time dilation is making the wire look like it's got an increase in density of the electric current. And then the second part of this is what's the view of the electron's view of the positive charges in the wire? Well, if the electron current is moving to the left, say, well, if from the electron's point of view, it sees the positive charges are moving to the right, and it sees them increasing by their charge density by the same amount. These are basically flowing, the same velocity, just in opposite directions to their view. So this is a graphic view of what's going on here. The top line here, the view of the positive charges and electrons in the wire, no current. Basically, you assume there's equal number of electrons in the wire as there are protons. And that's not quite true, but that's going beyond this discussion. So when the electric current starts to flow through the wire from the positive charge's perspective, the electrons in the wire with electric current looks like their charge densities are increased. This is a graphic view here where I show that the electron now looks like, the electron density looks like it's greater. It's from the proton's view in the wire. And these are two wires here we're using. So we have two currents flowing in the same direction. And then the bottom diagram here shows the electron's perspective, which shows the electrons as being stationary because they don't know they're moving, because you don't really feel velocity. And they see the protons moving in the opposite direction. And this is nothing new here. This is just basic, the source of the magnetic force. So, but what happens here is we have a number of interactions going on here. You know, we got the protons in the wire at the top seeing the Lorentz contraction of the negative charges in the other wire. We got the protons in the bottom wire seeing the contraction of the electrons in the first wire. Then we have the electrons' view of each other since they're moving together. They just see the same repulsive force that they would normally see stationary. And the same thing for 6, the positive is stationary, so they see a repulsive force in the positive charges. And if there was no current here, we would just have 5 and 6, and they would be exactly they would be the same as if they were moving, because they don't really see each other's, they don't view their own motion. But then we got the second part here is we also have the electrons from the second wire seeing the protons, and then the electrons from the first wire seeing the other protons. So we really end up having 6 interactions that we really got to model, where in an electric current, 2 of these interactions, 1 and 2 and 3 and 4, are basically the same. But what we don't have here is we don't have a magnetic field. We got a complex interactions from charges in different inertial reference frames that you have to take separately. And then what you do is you use a mathematical method called convolution, and you co-evolve them together to get the magnetic field. And you would use that to, you would use the properties of a wire. So properties of a wire conductor would be a long, thin wire that's tubular, whose drift velocity is, 10 millimeters per second, say, for a certain current. And you would end up modeling all 6 of these forces together, and then they would get co-evolved together, which is equivalent to summing them. So now there's also something called Green's reciprocity, which basically says that the forces from the electric field and multiple potentials in the same inertial reference obey the rules of superposition, which basically says, and this is based on Einstein here, is I have charges in one inertial reference frame. So I'm in the stationary reference frame, and I'm looking at an electric current flowing in a wire. I'm going to be able to take that view and sum all the fields together, say the electric field, and I should be able to get the forces from that inertial reference frame. But if I go to the view of the electrons that are moving in a current, and now I'm looking at, instead of looking at the electrons moving, I'm looking at the protons moving. Now I have to redo all those force equations because they're only going to follow the rules of superposition in that inertial reference frame. So if I have 2 wires flowing electric current flowing in the same direction, I have to take my total fields and I'll sum them together from the stationary point of view, and then I'll sum them together from the electron's point of view. And then what's going to happen is I'm going to have a difference equation there. And that's what gives us the magnetic force. So for Green's reciprocity to be valid, all the charges must be in the same inertial reference frame. For electric fields, that would mean that all the electric charges must be stationary. Fields of charges in different inertial reference frames are going to break Green's reciprocity. An example would be the stationary charge fields do not follow the rules of superposition for other charges in the moving frame of reference. Just because I use the example of just two currents with the same drift velocity, but say we had 20 different wires made of 20 different materials running at 20 different drift velocities, and say some of those wires are moving, which inertial reference frame do you use? You can't. You got to take the view from all of them and then sum them together. So a wire might be moving with a velocity. I'd have to calculate the forces on that wire by taking its view of all the charges. And another wire moving at a different velocity, I would have to take the view of all the charges from its inertial reference frame or its velocity to calculate the force on it, because the forces on those two wires could be different because they're moving at different velocities and the drift velocities in the wires are different. But that's all taken out of electromagnetics. When we use those simplified equations, the vector equations that Heaviside and Gibbs did, these types of interactions have all been written out just because it was too much math for what they were trying to model. Magnetic fields from magnetic currents and copper conductors only follow the rules of superposition for currents and other copper conductors in the same inertial reference frame. If the conductors are moving, all of a sudden you've got to take both those two views into account. Magnetic fields from electric currents and other materials, as in graphene, will not follow the rules of superposition for electric currents in, say, copper, because we'll show it here in the next slide. So this is an example of just trying to do it from two forces. If the wires are made of copper, they're moving the same drift velocity. Force 1 plus force 2. The total force is going to be force 1 plus 2 minus 5 minus 6 plus 3 plus 4. But now if the two wires are made with the same drift velocities, they're basically going to be the same force. And the protons are going to be at their same velocity because they're stationary. So they are going to be equal. And the drift velocity of copper, 1 to 10 millimeters per second, which is really slow. So you don't see a lot of strange effects from copper. Now, this is mathematically how we would do it. The top line is wires with no electric current, basically says all the fields from all the electrons and protons are basically all going to be equal, and they're going to be opposite of one another, such to the point that the wire will be neutral. So because you have two sets of negative charges here and then two sets of positives, and the electrons are offset by the protons. But once you have an electric current, the drift velocity of 1 and 2 changes now, and we're assuming they're the same because we're using the same materials. They're not going to be equal to the same drift velocities as the stationary protons. So from the proton's initial reference frame of view, for Green's reciprocity is broken because the two protons are equal from what they see, but now these electrons, V1 and V2, they're moving. So their current density or their electric field now is increased. So stationary, the wire stationary, when they were stationary, the electric fields were exactly the same as protons. So they basically summed to 0. And you just, the wire stayed neutral. But when we have electric current going through them, from the stationary point of view, the wire is not neutral anymore. It sees the density of electrons being greater. But then for the electrons' inertial reference frame, or from their view, you see the exact opposite now, because the protons still see them as the same, but the electrons do not see the protons as the same, because where in the stationary point of view, you don't have any Lorentz contraction here on this term, but when we look at it from the electron's point of view, now we do. And this is the source of the magnetic force, which is the magnetic field is trying to model. So for copper wires, the force is reduced really to one force because we have 1, 3, 5, 6, and 1 and 3, 5, and 6 are virtually going to be 0, just because 5 and 6 they're not moving, and 1 and 3 are just the same as having 2, or the same as 2 and 4. So the total force in the wire ends up being 2 and 4, where 2 is going to be equal to 4, which means if I go back here, the force here from this wire to here is going to be the same as force going over to here. Which basically translates into the fact that the force on one wire is going to be equal to the force on the other wire. So force F1 and F2 get added together, and then you get basically 2F2 or 2F4, which gives you the equation for a current that we see today, which is totally valid. But now if we start using two materials other than copper that don't have the same drift velocity, again, we have the first line up here on the top where everything's equal. All the charges for the electrons equal to protons except their opposite signs. But now we got two wires of electric current. So one wire is drift velocity 1, I'll call V1, and the other one is drift velocity V2. Well, they're not equal now, even though the protons are still the same. So then from the proton's inertial reference frame, Green's reciprocity is broken. The two protons are equal now, but now the electrons moving at velocity 1 don't equal the protons, because now their current densities increase by some amount due to the velocity. But then the other wire has a different one, V2, so their density is going to increase by an even different amount. So here's a case where which inertial reference frame would you use for the electron's inertial reference frame? Do you use it from V1, those electrons, or do you use it from V2, those electrons? Because obviously then if these velocities are different, then the force from them is going to be different. So again, we have, so in this case here, F1 plus F3 minus F5 minus F6 is not going to be 0, because F1 is not going to be equal to F3, even though F5 and F6 will still be equal. The total force then isn't going to be F2 plus F4, because F2 is not equal to F4 anymore. And the total force F2 plus F4 is not going to work for our equation that we calculate the magnetic field from, or the magnetic force on two wires. It's easy to perform that if I had a wire of copper, or an electric current going through of say 1 amp, and I had another wire, say of aluminum, the electric current going through it of 1 amp, I'm not going to have the same forces on those wires as I would with two copper wires. And that's written out of today's equations. Okay, so when does the magnetic field of electromagnetics fail? Well, when the rules of superposition are not valid, which basically says when there are more than two charges in different inertial reference frames, or we're using materials that have drift velocities in two different directions. Well, the drift velocities in the material that the electric current flows in, they're different. So that would be the materials. The other place the rules of superposition wouldn't really follow is you had 3 or more charges moving at different velocities than one another. When there is no conductive path to earth ground. I'm going to show here that one of the problems with electromagnetics is really dependent on having a connection to earth ground. Because really, on these examples I showed here, if you have a conductor that's neutral with no electric current flowing through it, and you put a current through it, all of a sudden the current density is going to be increased from the stationary wire's point of view, so you should see the wire to be negative. And you go online and try to get people to explain that. You never really get a good explanation. So we had to do an experiment to show what really happens there. And the other thing is power sources having infinite impedances. If you have a power source with infinite impedances, all of a sudden electromagnetics is going to start to break down, and we'll show that later. Okay, so we're back to this thing here. The view, like I just described, the view of the positive charges and electrons in the wire when electric current is flowing from the wire's perspective and the stationary reference frame, the apparent charge density of the electrons is now making the wire to appear to be negatively charged from the stationary point of view. Which, that's not in the equation for the magnetic field, right? It assumes the wires stay neutral. Because if your wires, when you flow an electric current through them, all became negative, all of a sudden the force between the wires is not going to be the same as when the wire is neutral. And that's where electromagnetics fails. So we had to do an experiment. So when a circuit's not flowing any electric current and is grounded to earth ground, this big sphere that's conductive, the static electric field measures 0 volts from the wire. And this is a little circuit here where we just have a battery with no connection to ground. We have a switch to open and close it. We also have a switch to ground. We have a simple electrostatic field meter, not a reciprocating type, because a reciprocating type is always taking a sample of the electric field and then testing it against a reference. And that does screw up electric field measurements. With a simple one, which is just really a FET that's driving a meter on a battery, you can see these kinds of electric field changes better, but they're much harder to use because they like to drift. So in this condition, we have 2 resistors of equal value. Then we have a little bit of copper conductor here in the blue that's set up so that electric field meter can measure the electric field from it, which indicates, the voltage on it or its potential. And when everything's all grounded, it reads 0. And we have no current flowing through it. So the experiment is when we allow current to flow through a wire, the wire reads negative when measured with a static electric field meter as predicted by physics. So the top here is the same circuit again, where it's open. So we close the switch, we open the ground connection, and we do these together. So we would open up the ground connection first and then close the switch. And current flows in the direction of the arrow. Well, when we have a simple field meter there, we do read that. We actually read the whole system increases to minus 1.1, say, for a particular current. This reading tends to be hard because what happens is once this system is negative, charges in the environment are going to start migrating to it and away from it to try to offset that current. So a reader, when you do this test, initially when you power on the circuit, it reads minus 1.1, but if you were to walk away, get a cup of coffee, come back, that reading will slowly drop to 0 over time because charge from the environment, the air, and someone walking across the room and touching the circuit will all screw up that measurement. So that being a hard measurement to do, a better way to do it is replace that with a Coulomb meter, because if the whole circuit becomes negative when a current flows applied to it, then a small amount of charge must flow to ground that you can measure. And that's what we did in the experiment under our DARPA project. We basically replaced our field meter with a nano Coulomb meter. It's placed in the same place between 2 resistors. It technically wouldn't matter where you place the Coulomb meter, but just to be sure that you don't have effects from the potential screwing up your measurements, we take it between 2 resistors or equal values so that if the battery's +1, -1, when it gets turned on, it won't change the set point between the 2 resistors. And the experiment itself is a little bit more complicated. There's more than one switch that gets closed, and they have to be closed simultaneously, but this is a good way to diagram it. So when we did this experiment, the current is flowing through the wire. When the wire reads negative, the Coulomb meter measures about 10 nanocoulombs of current of charge flowing to ground. And it measures that when you flip on the switch, it instantaneously measures that, and then it's no more current flows to ground. And then so what you do is you open up the circuit, and then you see the same exact amount of current flowing back into the circuit, which validates the view physics has that the wire's charge density increases from the stationary point of view and makes the wire negative. Because that's what the Coulomb meters are telling us, that the wire really does become negative if you don't have a connection to ground. Now, if you had a connection to ground like a Coulomb meter or an indirect connection, when you flip the switch, the wire would stay neutral. And now electromagnetics starts working because that's what it expects when you calculate the magnetic field. The forces between 2 wires, as the wires stay neutral, will be the same. They won't be affected by the wires going slightly negative. So this is one of the requirements electromagnetics needs to correctly model fields and forces is we need a connection to ground. Now, when this experiment was done, this is our test system here. The head down here is where we put a conductor, and we're all battery powered, and we have coulomb meters here to measure different things. In this test setup, we actually have two ribbons. We have a reference ribbon that has a reference current going through it, and then we have a test ribbon that's very close to the reference ribbon. And so what we would do is we would basically have the reference ribbon powered or unpowered, and then we power both the ribbons together and then both ribbons separately. So if we have a copper ribbon that's powered, has a current going through it, and then we have a copper ribbon next to it that we put the same amount of current through it, and both those two current ribbons are isolated, what we get here is when we close the contacts for the test ribbon, we see that 9.9 nanocoulombs of charge flows to ground. But in this system, our test ribbon also is on too. So we don't have any, that ribbon now is slightly negative. So then we will test the test ribbon and see how much charge moves from it to ground. And it will move 5.5, which is about half of the charge that the test ribbon put out. And then we would actually turn off the ribbons and see how much charge moves back into the ribbon, which in this case is 4.9, which is close to 5.8. You know, these measurements are a little hard to make because they're kind of small, but the total charge, and then the other test we do is we see how much charge is transferred between these ribbons. So if I have two copper ribbons made of the same material with the same exact shapes, and I both power them with no connections to ground, I would assume that no charge would move between the ribbons because they would both be at the same negative potential. And that's what the last column is here. The total charge between ribbons is almost none. And, you know, it's a little bit because you can't make things perfectly. So we did this experiment with a number of different materials with different drift velocities. Here's the results from them. The top line is the same test we did that I just showed you, but we would replace the test ribbon with, you know, monolithic graphene, 50 micrometers thick. It's the same shape, same current flowing through it. We compensate for any resistance in it by adding a resistor to the other ribbon. And what we see is, okay, so we have less coming to ground. And then when we connect the test ribbon, we have less. And then when we disconnect the test ribbon, we end up having another funny amount that flows back in. But the total charge difference between the two ribbons now is only 1.2, which says, okay, there's something going on here. So we go to a different material. This material is a silver epoxy composite. It's 0.1 millimeters of silver spheres, you know, and they're put into the epoxy in such a way that they're equidistant from one another, just like you're making a high dielectric capacitor dielectric, except for the fact we add so much silver to it that we cross the percolation limit, and now they're conductive. So what that does is when we do the test again, we see 18 nanocoulombs flows to ground. And these are the same shape. The charge flowing back or flowing from the test ribbon is still 6. The charge transferring back to the test ribbon is -6. But now when we do the two ribbons together and we just power them on with no connection to ground, and we, you know, we put a coulomb meter in between them, we have 5.7 nanocoulombs that now wants to flow into the copper ribbons. That basically says that you know, the electric potential of the test ribbon has to be greater than it is on a copper ribbon. So then we went on to another one here, which we did the same test using 8-layer CVD graphene, and that's very thin graphene, which should technically be a little significantly thinner than the copper strips we're using, but they're basically the same shape. And now we still get a difference of 15 coming off of the test ribbon, but now, or the reference ribbon, and then we have 19 going to the test ribbon. And then we have 3 coming to the test ribbon. So we redo this test again, where we power both ribbons with no connections to ground. And then we see how much charge transfers between the ribbons. So now we see 7.4 coulombs going in the other direction. So something's definitely different here. So when you use different materials, even on the same shape type of ribbon, you're going to have either a force that wants to push charge off the ribbon to another ribbon, like a copper ribbon, or you're going to have a force that's going to want to push the charge or pull charge onto itself. So this would kind of imply, if we were to take this, silver composite and the CVD graphene and put them close together to one another, and we powered them with a battery with no connection to ground, and we didn't let the charge migrate between these two ribbons, then we're probably going to see an external force from these, because one ribbon is going to try to push charge out and the other one's going to try to pull charge in through a different field component. So that gave us, gave us impetus to keep moving on. We tested a number of different materials, not just these. These are some examples. So if the charge moves differently from these two materials, the magnetic field that each one of these two materials must be seeing from the other one must be different. And it's different because the drift velocities in these materials are different. They're radically different, especially for CVD graphene, which is flowing current at 10,000 meters per second, and copper is doing 10 millimeters per second. So there's definitely the two fields from these two, or the two magnetic fields from these two ribbons are definitely much different. So, which comes down to the other thing I have here is amps, right? Because an amp and a copper conductor is the same as a copper or as a CVD ribbon? Of course not, but of course it was like that in Riddick, I guess, the movie. So, and that's what electromagnetic says too, but it's wrong. So electric fields and charges only follow the rules of superposition from other electric charges, only if they're in the same inertial reference frame. Magnetic fields from magnetic currents only follow the rules of superposition for electric currents, only if the charges that compose the electric current are in the same reference frame, which basically means that the drift velocities are the same. Magnetic fields for magnetic materials follow the rules of superposition for all other magnetic materials, because, I basically say only if the line magnetic moments are in the same shell, because, basically when you model the electron flowing around an atom, it basically is moving at about 200,000 meters per second. So if you have magnetic materials that are the same, with electrons flying around the nucleus at the same speed, they're going to follow the rules of superposition. But the magnetic fields from magnetic materials are not going to follow the rules of superposition from a conductor, because the conductor is not moved, the drift velocity through the conductor is not the same. And I'll go over that here in a little bit. Magnetic fields created from changing electric fields that follow the rules of superposition for all other magnetic fields. Well, they don't. And a lot of people wrote papers on that the changing magnetic field generates effects that people can't explain, but that's beyond this discussion. Electric fields are created from all changing magnetic fields that follow the rules of superposition for all other electric fields, and that's not necessarily true either. But that's beyond this set of PowerPoints. Okay, so is the magnetic field from a magnet the same as the magnetic field from a wire? Well, so electric current of wires here, drift velocities are 1 to 10 millimeters per second. So, but a magnetic moment, this electron here is moving, at 200 meters per second. So, a straight wire is definitely not going to have the same type of field description as an electron moving around in an atom. I mean, you could take this wire and turn it into a coil and form it. You would have something close, but even then, these fields, if you were to break them into their components, are not going to all follow the rules of superposition. So this is the comparison of a current flowing through electric current and magnetic moment. So basically, the wire is equivalent to an electron circling the atom, except that the electron now is moving at a much greater speed. So, and then current loop produces a magnetic moment, just like a coil of wire, and it experiences torque just like a coil of wire. And so you can model it just the same with a north and south as you could model a coil of wire with a north and south. But is the magnetic field from a magnet the same as the magnetic field from a wire? Well, so a copper wire with drift velocity of 0.01 meters per second is going to take the equation that we use to calculate the magnetic force, and it's going to give us this number for everything underneath at the bottom of the fraction, which is going to be 1 minus v squared over c squared. And that gives us this number. Well, when we do it for the atom, magnetic material with electron velocity here, we're getting a much different number here. I mean, these numbers are different by 200 million times. So these two interactions are not going to directly sum. And you can see that where, a current will be, coulombs per second, and a coulomb is like 6.23 10 to the 23 atoms or electrons. And a magnetic material that doesn't have that many magnetic atoms aligned in a magnetic moment. So the number of atoms in a magnetic material aligned are going to be a lot less than is in an electric current to give the same kind of forces. And that there is written out of electromagnetics too. So electromagnetics must be a special case of a broader mathematical framework. One models the magnetic force from potentials, which means we have to break down the forces into the individual components, and then co-evolve them depending on the inertial reference frame that you're in. But problem is physics. So we got physics here. This is an electromagnetic tensor, and we got these things called B in here for a magnetic field. Well, what's that magnetic field created from? I mean, the way physics is designed today, the magnetic field that we use today is based on the electric current flowing through a wire. So you're going to take the properties of a copper wire, and you're going to start putting them into this electromagnetic tensor. And now all of a sudden you can't solve problems like maybe unifying gravity with electric force. So we'll go on. So we have to rewrite Maxwell's equations in a way that removes the magnetic field, because the magnetic field can be generated from all sorts of different charges and different inertial reference frames, and just gives us an electric field component. Because James Maxwell unified the electric field with the magnetic field. We should be able to do the same with gravity, and toss that magnetic field. So this is the modern way it's done again, except now it's being done from a different potential, and we're using the relativity, V over C, for the potentials and how those potentials change. And I don't expect you to know how to do this, but the resulting equations now, when we do this derivation, which is really the same as Maxwell did, except now we're doing it in a general case and not especially for a wire conductor, we get three equations. We get the electric field equation. These we have these two terms, which are the same ones that were Maxwell's equations. But now we got this one, which is known as Lorentz force, that we can use to calculate the magnetic field from. But now we also have the scalar potential again. So now we got this thing. Of course, we don't need to gauge it out now, because now we have the units for it. It's volts. So that says we should be able to measure this with an electric field meter, or we should be able to have it somewhere like around a coil and be able to move a wire into that, near that coil, and start to see, charge move off it or move on it. So now we got a complete mathematical description you can generally use to unify the magnetic field or say gravity. But so let's try Maxwell's method of doing it. So this next field is just saying we still have the electric field here, and this correctly models electric fields. And now we have this scalar electric potential. And what happens is that's tied to a point in space. So when it's tied to a point in space, it's tied to an inertial reference frame. So you have to multiply it times your inertial reference frame that it was created from. So if it was created from the stationary one, your inertial reference frame would be 1 because it's the same. And what would happen is now all of a sudden this scalar potential gets converted into volt seconds. And volts is just a potential, and seconds is telling us that we can build up that potential. So we could probably apply a scalar of a point over a period of seconds, and we could build it up from 1, 2, 3, 4, or how many volts we want until it starts interacting with the environment. And this is a new field component. This has been gauged out of electromagnetics. And this is one of the reasons why, you know, these types of devices we're trying to build have been considered to be impossible because we need to have two types of interactions, you know, one that, you know, one material that sees one field component and another one that sees a different field component. But electromagnetics is gauged out that different one. So electromagnetics says we're never going to be able to do field propulsion. So let's use our new mathematical method to, you know, create a magnetic field, because we should be able to create a magnetic field. So the magnetic field is just a cross product here. To convert the potentials into electric current. So this would be our standard magnetic field equation that's known as Maxwell's equation. It's really a cross product of the magnetic vector potential. And the magnetic vector potential is really based on the current. So current again is amps, which is coulombs per second. We know that's not going to work because we have to include the velocity. So we take coulombs per meter, and then we just multiply it by the velocity, right? So that we get the velocity coulombs over meter. So that's a simple operation. And we have these constants here, and we know the potential of volts, say, for one electron, because we'll just do this for one electron, because it's easier for the math. Would be Q over 4 pi ER. So that's basically the potential for that. So what we can do is the potential here is now replaced by our volts, because, you know, our potential is volts here. And then we just have to multiply it times V over C, because that's going to give us our magnetic vector potential. So then we're going to just do which is going to be this here. So then we just end up doing the cross product through these operations. I don't want to go over these because they should be obvious if you work with electronics, I guess, or fields, but they end up generating the equation on the bottom here, where the cross product is really equal to this equation, and then this equation is really equal to this equation. So we technically have created the magnetic field from our new model, but now our new model says, wait a second, if V over C is different than the drift velocity in copper, our magnetic field is going to change. So if I had a material that had a drift velocity of 1 meter per second, and I was moving the same amount of charge through there as a copper conductor moving it at 10 millimeters per second, you know, even though the amps are the same, B is going to be different. So that's kind of showing how Maxwell's equations are strictly tied to copper conductors and using materials that have very slow drift velocities. So then we should be able to do the same thing with the electric field equation. We should generate Maxwell's electric field equation, which is the black here, or the red here, which is Maxwell's potentials. And the top one here, the black one, is ours. And we can use the same tricks through here, where we can convert our constants into a form that gives us the same equation that we use as Maxwell's equations, or Maxwell's potentials, because it's really just a change in constants. And again, this operation clues it into the fact that, you know, Maxwell's equations using the magnetic vector potential here is totally based on the drift velocity of copper. Oops. Okay, so now we get to our scalar electric potential equation. So now what does it mean? So I'm only going to deal with the first term. It's the second term, and it's a whole nother subject. But the first term here basically says it's going to add to the electric field of a charge that's approaching you, like an electron flowing down through a wire. And it's going to subtract from the electric field from the electron that's moving past you. So it's moving away from you. So if you had an electron moving through copper, you know, a positive matrix like a wire, you know, so the protons now sitting in the middle of the wire are going to see the electrons that are coming to them as being a little bit more negative than the electrons that are moving away from them. Let's see. There's modeled here, electric current and wire. So this would be the wire model with no electric current. The electrons are just kind of bobbing around in there. And this is kind of showing that where you have a free electron in a conductor that's randomly moving around in a wire. And so the bottom one, oops. Yeah, so the bottom one shows the electrons moving through the conductor. So as the electrons move from left to right, these positive ions here, these positive ones are going to see that the electron's a little bit more negative here than this one sees when it's leaving. That's what that scalar effect is telling us. And that's been written out of today's equations in electromagnetics. So what this is also saying that if we have an electric field here that across here that he's seeing the electrons going to him a little bit more negative, then leaving him is a little less negative, you know, we should have an electric field component from the stationary view that's going to force these protons to move in the opposite direction of the current, a drag force, you might say. That's written out of electromagnetics today. So here's a graphic example of it. So using this model from, this will be the positive ions in the wire. As the electrons approach them to compose the current, it'll be a little bit more negative, and as they recede away, they'll be less negative. This says we should have a force in the wire that's going to be a longitudinal force in the wire. That's really going to be dependent on how long and how straight the wire is. And at this point, electromagnetics says wires don't experience longitudinal forces. So why don't we observe them? Well, actually we do. These are 5 papers out of dozens that are printed that says we have longitudinal forces in the wire. And these longitudinal forces can tear a wire apart. They either be a lateral force or a force that actually puts stress in the material of a wire. Example would be this one here. What they did to measure these longitudinal forces is they would have a wire sitting in a fixture and they'd have a spark gap on either side. And what they would basically do is they would apply a potential to the spark gap, and the electric current would jump the spark and then flow through the wire. And then the wire would break up in individual segments. And that breaking up of the wire is not predicted by electromagnetics. In fact, it says electromagnetics should not do that. There should not be any kind of drag force in the wire that would break it apart. But this new model does, and it does explain these forces, which kind of confirms that we really need to be not using the mathematics that describe a magnetic field, because we're limiting the types of interactions we can model. So let's go to implementation, because really, you know, all this theoretical stuff that people put out is just kind of, you know, whatever. If you can't build something from it, then it doesn't mean anything. So this is how you implement it. I can't get my thing to flip that well. There. Okay, so I'm having problems with my computer. There. Okay, so what we want to do is we want to make a block or a thing. We're going to have 2 conductors in there made of 2 materials that are different, that have drift velocities that are different. What we want to do is we want the currents go in the opposite direction, right, in the materials, because, you know, a good way to get the currents not to follow the rules of superposition is have them go in different directions, right? Especially when you're using a, you know, a stationary thing. Again, that's written out of electromagnetics. So electromagnetics says currents flowing in the opposite direction in conductors is going to be the same kind of forces or the same magnitude forces as currents flowing in the same directions. It's just one's going to be attractive and one's going to be repulsive. And then, so since we need to keep them separated, we're going to need an insulated sheet here. And then we don't want to use a wire. We want to use a block of some kind, because you want a large surface area, right? You know, a wire is not going to give that much force, but something with a large amount of surface area is. And of course, these power sources can't have any connection to ground or, you know, or even chassis. So if A and B are made of the same material and are powered by modern power supplies, which is a modern regulated power supply with connection to ground somewhere, material A equals B, we're not going to see any external force. You know, and I put it in a non-conductive matrix to make sure we don't have charges migrating from somebody touching it or moving from, you know, the environment somehow. Yeah, so how can we create an external force? Well, one thing, we can't create a force from nothing. We must take existing opposing opposite forces inside an assembly and turn the force vectors in different directions. So what we're trying to do is say we had two conductors, they're flowing electric currents, and they had a repulsive force between them. So we got two force vectors, one on one wire, one on the other. You know, we don't want to generate a force. We just want to take those two that are normally opposite each other and just turn them a little bit. Because once we do that, if we turn them in opposite directions, we're going to start getting an extra force on the assembly. Okay, so to do that, the conductor that made of A material must observe a different field than B material. Well, we can do that because fields of charges in different inertial reference frames don't follow the rules of superposition. They will use this fact to use materials with different drift velocities that will cause the electric current in model A and B to observe different forces from the other's materials. And the other trick is to have them go the other opposite directions. Okay, and again, we can't create an external force from assembly using electromagnetics because electromagnetics only has the cross product terms from Maxwell's equations. It only has the perpendicular force. Electromagnetics, only the static field components generate an electric force. So we can't generate an electric force from anything else except electric charge. The magnetic scalar potentials are all gauged out with Lorentz and Coulomb gauges and produce no forces, so you can't use them. Changing magnetic field does produce an electric field that could be used to produce an external force. Again, this is beyond this paper, but yeah, it looks like it can. So magnetic materials produce a magnetic field that follows the rules of superposition with magnetic field from electric currents and conductors and such. We can't produce an electric field or an external force either. That basically, electromagnetic says the magnetic field from a copper conductor is the exact same thing as a magnetic field from a magnet, and they're just going to sum at any one point. You have no opportunity to have, say, the magnetic material observe a different field interactions than, say, the copper conductor. That's not allowed in electromagnetics. But sure, with this new mathematical model, we could produce an external force from current elements using this new model. You know, we have 5 field components here instead of 2, you know, electromagnetics to create forces from our assemblies. You know, these 2 new field components are longitudinal field interactions that produce longitudinal forces. And these new longitudinal field interactions can now be used to turn a perpendicular force vector into one that has an angle on it, because if you have just electromagnetics, the cross product term generate a vertical force, and electromagnetics doesn't allow a longitudinal one, you can get a material to generate a longitudinal force along with the vertical force. Now you've turned that vector by an angle. And these new field interactions give us the opportunity to allow one conductor to observe a force vector that is different than another conductor to produce a total external force on an assembly. These new field interactions allow us to take the perpendicular force from one conductor and have its reaction force be a longitudinal force or a transverse force, which would be force in the material. So you basically would be able to take an assembly that generates an external force, and then its reaction force would really be absorbed by the material. And that's all been written out of electromagnetics. So if A and B are made of different materials and shapes and they're powered from separate sources, our model says we can generate an external force. You know, it won't necessarily be vertical because it's going to be a sum of the vertical and the transverse and the longitudinal forces inside the materials. I represent that as yellow, red, and these 2 vertical forces. And this would be for material A and B not being equal. And so this new model allows us to create 3 types of forces: the perpendicular one, the longitudinal one, and the lateral ones, which are forces in the material. So the perpendicular force is created from the cross product term. That's really just a magnetic force, or that we use the magnetic field to model today. You know, the magnitude of the force is proportional to the drift velocity, charge density, and the shape of the conductor. The cross product terms are not affected by the longitudinal field components, which means they don't follow the rules of superposition, which means you just can't take a field component from the longitudinal and just sum it with the one from the cross product, because they're created in totally different inertial reference frames by different methods. Charges in different inertial reference frames exert forces that don't follow the rules of superposition for charges in other inertial reference frames, right? So you use materials that have different drift velocities. And forces created from the cross product terms are modeled by the magnetic field. Okay, so the longitudinal forces created from the scalar electric potentials, or the dot product terms, that are now gauged out electromagnetics. You know, the longitudinal force is opposite the current flow. The magnitude of the longitudinal force is proportional to the drift velocity, charge density, shape, and length of the conductor. The longitudinal force components are not affected by the cross product terms. The scalar potential is different when viewed from different inertial reference frames, which means you could generate a scalar potential that might look different from another moving past it as compared to standing still next to it. And yeah, the forces created for the dot product terms are gauged out today by the Lorentz and Coulomb's gauges. Now the lateral forces are created from the dot product terms too. The lateral forces are the stresses observed inside the conductor. The magnitude is proportional, same to the drift velocity and charge density. It really doesn't have anything to do with the length of the conductor. You know, lateral forces are affected by the longitudinal components and the charges inside the conductor. Charges in different inertial reference frames exert forces that follow the rules of superposition for charges in that conductor, but not another conductor that doesn't have a connection to ground or connection between them. The lateral forces are observed by a conductor and not addressed in electromagnetics. And an AC standing wave electrical potential, since it generates a field that's an electric field, that electric field will interfere with the electric field inside a conductor. So you have a battery that's hooked up with a conductor, and you'll have a current flowing through it. And if you have a scalar wave flowing over it, when the one side of the scalar wave goes past the section of wire, it'll make the wire look like all of a sudden its resistance has dropped to a low value, or maybe even go negative resistance. But then when the other side of that wave goes past it, all of a sudden, if it's large enough, it'll counteract the electric field inside that part of the conductor, and electric current will just stop flowing in that electric conductor. And if you're generating a standing wave, you know, knowing that an electric circuit like a 12-volt car is always a circle, you know, if you had a standing wave and that circuit got near a standing wave scalar electric potential, all of a sudden it would stop working. All the electronics and everything would just stop working until that potential was turned off or moved away. Okay, so now how do we do these strange effects? Well, first thing we got to do is, you know, we can't have connections to ground. We can't even have indirect connections to ground, you know, which means you can't have charges migrating from the environment to whatever you're working on too. So things got to be sealed up. You got to have multiple, you know, cages, you might say. And like a Faraday cage is not going to work because a Faraday cage is a connection to ground. So, you know, what you need to do is use another whole different technique to shield these kinds of things, because if you have a scalar potential, it's going to move right through a Faraday cage. It's not going to even be affected by it. It'll generate a little bit of current inside of it, or maybe current to ground, but it really won't be stopped. The other thing you got to have is no source impedance, because if you're going to see longitudinal forces, say across the conductor, that's going to produce a potential at different sides of that conductor, and then the source impedance is going to drain off that difference. That's why on those papers that were able to show that there was a stress inside the wire when they applied a current through it, they had to use a spark gap, because they couldn't connect the power supply directly to it, because the power supply would just, you know, basically melt the wire. And because they needed to decouple the source impedance from the material, or they wouldn't have observed those longitudinal forces. And the other thing is, gotta stop using copper wires, long, thin copper wires. You know, they're not going to work for anything. I mean, you can use them in small segments here, but, you know, I'm going to show you how to get around that. Okay, so first thing is, you know, take your material, whatever it is you're going to use, and put it in a non-conductive matrix of some kind, so that it doesn't allow charge to migrate to it, and then power it with a battery. You know, a battery for sure doesn't have a connection to ground. So That's the easiest way. But the problem with the battery too is it still has a source impedance. I mean, the battery's going to do the same thing. If you had a material that was generating potential on either end of it, you know, the battery's either going to put more current into that conductor or less current, which is equivalent to draining it off in a source impedance. So you won't see longitudinal effects by just using a battery. So you got to get rid of that source impedance. Well, one way to do it is, you know, to use these things, you know, these types of machines, because, you know, they use a charge bucket brigade like here, where they actually put a charge on a piece of conductor and then move it to another conductor that powers your device. So, or a Van de Graaff generator or an influence machine will work well too. But the big problem with these guys is they don't generate a lot of current unless they're really big. So that puts them out. But that is the idea. You need to have a no physical connection to your power source. There needs to be a space in there, a vacuum, something that disconnects you from the properties of the power source and the copper conductor wires. Well, this is the other way to do it, use an electronic tube. Tubes are great. I mean, they have a vacuum in there. In fact, this tube is a dual diode made in Russia. Russia still makes tubes today. You know, the attitude in the West is, you know, there just must be backward technology and they don't know what they're doing. But the reality is they found a use for them. This is what a tube is. So an electronic tube uses an electron emitter and a collector. They're separated by a vacuum. So electrons boil off the cathode to the anode. I mean, you can use indirect heating, it just complicates things. So if we wanted to isolate our source impedance from our current elements, we're just going to use a tube, and we're going to power it by battery, of course, because we can't use a power supply or nothing connection to ground. And then I put plus here, but that's where you hook the negative lead of your, say, of your power source. And then the negative charge will move up here, boil off in the collector, and then go to your load. And then you would use the same circuit, a different physical circuit, but the same type of circuit on the other lead. So you would do this with these tubes here. So now you have a battery, it has a source impedance, but it doesn't really matter because now our load doesn't see the source. It doesn't even know anything about the source. It's decoupled with this vacuum here. You know, it's just this emitters taking electrons and sending it to the source, and then vice versa here. So that's figured. So once you've done that, now you have the opportunity to observe longitudinal forces or the dot product, as those papers had, where they were observing lateral forces in the materials. In this case, sure, you also will be able to now see a longitudinal force in the entire system. But we still have the problem of long, thin copper wires. So, you know, we use copper wires for everything to power everything. So we have to get rid of them. Well, just to go on, tell you what we're trying to power here. Different current elements are used to amplify different components.
Richard, yeah. I was going to say there's some papers that people might want to look up where rail guns were displaced laterally during experiments by huge amounts, and they couldn't figure out why. And anyway, it's relevant.
Yeah, no, thanks, Eric. That is from these components. So the force that Eric's talking about is the one that we're modeling here and the one that we are able to reproduce fairly effectively. So then the types of current elements we want to use. Well, this is CVD graphene. So, you know, it's great because it's got drift velocities in the range of 10,000 to 80,000 meters per second. So you're going to get a lot of effects from something like this that if you had a piece of chunk of copper on there, you're not going to get. And then that's good for generating cross product components, which is equivalent to magnetic field. But now to generate the dot product components, since they're longitudinal, you need to have something with thickness, not thin. So this is graphene aerogel. So aerogel has the same properties. It doesn't quite have the same kind of drift velocities, but the real advantage it has is it has thickness and it's extremely light. And it's extremely conductive too. And then what you can do is you can add lots of other materials into it to enhance its effects or forces. And that's what we do. So CVD graphene is a current element, yep, high drift velocities, the sheet resistance, which is also important in these. Copper conductors virtually have a sheet resistance of near zero. But these will have between 300 and 400 ohms per square, which definitely enhances cross product terms, which we'll go over later. Different shapes than a wire. It's not a regular wire. It's a great big flat sheet. Great big flat sheets are going to produce the greatest cross product terms in the center of them. And I'll show you that later. And it's the thickness. One layer is just a few microns thick. So if you're going to get some kind of amplification of the cross product terms, it's going to be greatest on a thin sheet like that. And again, to start seeing these kind of effects and not just a magnetic field from the sheet, you need to keep charge migrating to and from the circuit being tested. And you can't, power this sheet with a copper pad. This is what it looks like. It comes in a carrier. This is on acrylic. The way the number of different companies make them that you can get from. A lot of times they're stored under nitrogen. That's why they're in a carrier. When you work with them, they usually have a acrylic cover on them, or a film acrylic on them that you have to eat off before you use them. But have found having them on acrylic substrate really helps, because acrylic is really smooth. So you could use the acrylic substrate as is if you want. Okay, now this is where I'm going to go on geometric amplification. This is where you generate large field components from the cross point. So an electric field line charge, if you had a line that had a charge, you're going to generate an electric field that's basically going to have the electric field be greatest near the center of this line charge. Well, on electric field, and that's basically using this here. So we had these charges across here, we would generate electric field up here that's greatest. But now we have a new term in here. We have the cross product. So that cross product now can be added to this just like it is here. So now we can have the potential in the wire give us a field that forms like a little tent, which is greatest at the center. But now we can have the potential moving through a wire. And so the potential will be moving towards us out of the page, right? Because we would be looking at the edge of the sheet. And as the current moves out towards us, we're going to see a much larger electric field change in the center now because of this component here. So the mathematics are pretty simple. You basically just reproduce or just change the charge with the potential, and you use the same equation. So the way this would work is I have this sheet that I'm flowing current from left to right. When I look at it from the edge, I'm seeing this geometric amplification of the electric field components from the cross product here in the center. If I look at it from the edge over here, I see the same thing over here, where it's just not quite as great near the edges as in the very center. And the amplitude of the electric field change is going to be represented in an equation like this. And this plot is basically this. And so one of the other things to notice is this is the same mathematical model as we used on the other page. The one thing you do notice is we have relatively large increases in electric field potential on the edges. And that is represented today. If you were to do a sheet of a magnetic field, they would say the magnetic field is greater at the edges too, but having it as an electric field makes it much easier to work with. Okay, so this is how not to power one of these sheets. You don't want to stick it onto a couple pads, because the pads are going to be conductive. They're going to take the sheet resistance near those pads of 300 and 600 ohms per minute per square and reduce them to zero. So you're really only going to see any kind of effect of the increase in the cross product is in the center of this. So you can't power them that way. So what we use is something called a directional composite. And there's a number of papers out there how to make them. And they're basically epoxies that you process them in a magnetic field or an electric field using, either magnetic nanoparticles or they can be micron particles of different shapes, usually, platelets or something. And you either put them into you know, an epoxy substrate that's high dielectric, and you keep adding them again, just like you would to you're trying to make a dielectric for a capacitor until you cross the percolation limit, and quickly the resistance of the material drops to a low value, and you can tweak the value what you want. And so what you do is you tweak the sheet resistance of these directional composites to be the same as the graphene in one direction, going, in this case, flowing from left to right, that it would be the same. But if the current tried to flow vertically, then they're going to encounter a much higher resistance, you know, by a factor of 5 or 10 times. So that takes the current and forces a current to flow across the sheet in a straight line. Because really, if it tries to flow from here down to here, the resistance is going to be greater on the sheet and in the composite. So this kind of forces the current to basically flow in a straight line through the sheet. And this top part here, this is the actual sheet that would be on a substrate. This would be the composite applied, and these would be your copper pads. And there's a low leakage diode there that I can't go into. And same thing over here. This is the copper pad, and the current would flow through here. And this will give you the greatest powering scheme to get the maximum amount of field changes inside this. And you'll get this way you have the actual field changes across the whole thing instead of just in the center. And, you know, schematically, it's represented a diode, directional composite, the sheet, the directional composite, and the diode. And this is an example of using an 8-layer CVD graphene sheet. The more layers you have, the more current you can apply through it. Okay, now we go on to using the other part, the other conductor or other material B, because that's got to be different. I can't use 2 of these together because they have all the same drift velocity and everything, and they're not going to get good results, if any. So the aerogel has high drift velocities too, and its volume resistance is a lot less. It's really a thick, rough block, which gives you, when you look at it from any one side, you have a thickness. So that gives you a whole thickness to generate a dot product term from, instead of just a real thin one, or like in a wire where you got a really thin wire. And when you look at the end of the wire, it's really small. So you really want to produce a block. And again, you know, power sources, no connection to ground, keep charge from migrating to the circuit, do not apply current to the elements using copper pads again, and do not allow source impedance to be observed by the block. And that's really critical here for this one, because using the tube isolators for a graphene sheet probably isn't absolutely necessary. You might get away without using them, but it definitely is necessary for a block like this. And this is what an aerogel block looks like. You know, it's very fragile. It's in styrofoam. You know, breaks real easy. It, you know, weighs almost nothing. And this is after we process it. You know, we basically to have a technique. We put high dielectric epoxy in there, a number of other components to enhance its performance. And we end up with a block like this. And so the way this works, so aerogel will amplify the dot product components to the electrodynamic field that are currently gauged out of electromagnetics. So same thing again, we have the dot product, the electrons moving here. You know, if I stood at this end of the block here, I'm going to see all these potential increases down the whole block. And so they're going to integrate. So even though the potential change here might be, you know, fractions of a volt, if I look at the block down here, down the whole end of it, I'm going to see tens to hundreds of volts, you know, basically negative. Now, same thing over here. If I was at this end of the block, since they're receding, each one of these might be a fraction, but I'll see tens of hundreds of volts here. And again, you have to use the isolators to see this, or a spark gap, or something that mitigates the characteristics of the source away from this. But then, so the other thing I point out, it's VS. So if I let this block run here, these potentials will start small, and they'll start increasing and increasing and increasing. So it allows this particular block to give a performance that it's not going to be, you know, turn on and see a force. You're going to turn it on, and then it's going to build up over a short period of time. And it'll build up to a certain value, because these potentials here will can only get so far, because eventually your isolators are going to spark over, or the charge is going to start leaking out somewhere. So the difference is only going to get to a certain point and stabilize, but it does take a few seconds for it to get to that point. So we do the same way. We're going to power it the same way. We have this block here, which is right here. We have the directional couplers here, and then we have a composite, and then we have the copper connection here, and then diodes here. And these are some of the things I can't talk about, you know, what these diodes are doing, because they're doing something really special. And basically the current's flowing through here. And it's the same, you know, schematic. And schematic doesn't represent what these diodes are really doing. Well, so what we would do is from the side view, we would mate these two together. We would have this aero block gel here, and then we would have our thin graphene sheet here. Then we'd have a directional composites powering them, and then we'd have the copper pads here. And so that would isolate these from, you know, our sources and our copper. Here's a panel or assembly that's already been mated. You know, you see the block here, and then on the other side here, which you can't see, is the graphene. And, you know, since we have everything isolated with these and some diodes that are incorporated here, we are able to use a copper wire to go to the isolators from here. And then and what this would look like, so we have all the elements necessary to absorb these new forces. So we're going to have a current source, you know, with source impedance like a battery, which is okay. We're going to use our isolators. They're going to isolate us from here. We are going to be allowed to use some copper wires here, but we want to minimize the length of them. And then the directional composites will be powering the panel directly. So this, when I say implementation, this is what you need to do to start seeing external forces from conductors made of different materials and powering them correctly. Because that's been really the problem most people have had with a lot of these devices that they're building, is they're not taking into account their power source or interactions with the environment. Because a lot of these devices people make, I've noticed that they seem to be kind of on the verge of working, but then maybe something will tick and then something will do and then they stop. Yeah, and that's just because of the fact there's charge migration and they're not powering them right. You know, a lot of these devices might work if they were powered differently. So this would be a typical run of what we make that assembly here. So we apply power to the assembly here on the panels. And initially we don't see anything happening because we already know that V over C is going to starting to build up on the aerogel. And it builds up here to a point here, which is over a few seconds. And at which point now the CVD graphene starts interacting with that aerogel. And then now we start getting a force going upward. The way this graph is set up is it's a weight of the test head. So this is actually measuring the weight. So this is the test head's weight at 0 with no power applied to it. And as the test head gets lighter, the plot goes lower. And we see this is just normal when we're dealing with these types of materials. We power them. We have to power them, we wait a few seconds, and now we see an upward force on this guy. And it gets to a point and then starts to ring a little bit and kind of drops down over a period of about a minute or two. And this particular plot is of 200 millinewtons, and that's really about 20 grams of it getting lighter. And that's on a test head is about maybe, it's less than a kilogram. It's probably half a kilogram. But even then, most of that weight is the acrylic assembly and the test head itself. So, these elements themselves, especially when we start getting the aerogel and the CVD and the directional composites, are pretty light. So if they're separate, who knows, might have them lift off the table, but it's too hard. We're not that point. And this is a typical run. And the power consumption of both these panels is only like 25 watts. So we get very little power. We're getting a good amount of force off these. And this is kind of just like a typical run. And, I kind of gone past the point of where I can present any more information. I can't show you the type of test jigs we use. I can't show you the power supplies we use because that's, that's going to basically, I guess how would you say, violate our terms, because on our DARPA project, we can release some information. We're not allowed to release things like how we're building things and how they work, but I'm giving you enough information. So you should be able to build these yourself and just start getting some results, because, you know, electromagnetics should have been updated a long time ago. So the one thing I always have to do here at the end is Newton's third law. Everybody learns a simple version of Newton's third law, but Newton's third law had to be modified after 1905 because of relativity. And Newton's law says whenever an object exerts a force on a second object, the second object always exerts a force on the first. The two forces are equal and opposite magnitude and opposite direction, and have the same nature. And they had to add that at the end of that, because if they didn't, then the magnetic force would be violating Newton's third law. So, and the meaning of nature is the same kind. So Newton's only hold respect to a certain set of reference frames called Newtonian or inertial reference frames. You know, and this goes on to say, you know, how this feeds back to the other two laws. So field propulsion without any propellant is not a violation of Newton's laws. Newton's laws have been modified to support that. It's just a lot of people have a lot of old ideas, which really kind of hurts development, because, you know, a lot of people might give you money, you know, believe the simple version of Newton's laws. All right, well, I'm kind of done.
Well, Richard, thank you. Thank you very, very much. I'm going to unmute everybody. You deserve an enormous applause, because that was a tremendous presentation. So let me unmute everyone here, and let's give Richard an enormous applause, everyone.